Have you ever looked up at a rocket launch and wondered what it really takes to defy gravity? Well, today, we're going to tear down one of the most complex machines humans have ever built, the launch vehicle. We're going right under the hood to see the incredible engineering that gets us to space. Let's dive in.
So this is the big question, right? How in the world do you take a very delicate, very expensive satellite and get it from a dead stop to over 17,000 miles per hour? That's 25 times the speed of sound. The answer isn't just one thing. It's a whole symphony of brilliant solutions to what seem like impossible problems.
It all starts with a principle you've known forever, Newton's third law. A rocket is basically just a tube full of stuff, and its only job is to throw that stuff out the back as fast as it possibly can. Think about it like this. If you're sitting in a rolling chair and you shove a heavy basketball away from you, what happens? You and the chair roll backward. A rocket is doing that exact same thing, just on a ridiculously powerful scale.
And this brings us to our first major villain, the Tsiolkovsky rocket equation. Honestly, it's a brutal piece of physics. It basically says that a rocket's final speed is all about its mass ratio. That's how much of its weight is fuel versus the rocket itself. To go faster, you need way more fuel, which of course adds more weight that you have to lift in the first place. This one single, unforgiving equation dictates almost every single choice in rocket design.
Okay, so our first problem is a big one. Just breaking free from Earth's gravity. You can't be subtle about this, you need overwhelming brute force.
The go-to solution for this is often the Solid Rocket Booster, or SRB. I like to think of it as controlled violence. A single one of these things, like the ones on the Space Launch System, generates a staggering 3.6 million pounds of thrust. Put them together, and they're providing over 75% of the total power needed just to rip the rocket off the launch pad.
And this right here highlights the first major trade-off engineers have to make. As you can see, solid rockets give you unbelievable thrust, and they're pretty simple. But the catch is control. Once you light that candle, it's going to burn until it's empty. You can't shut it down. Liquid engines, on the other hand, are way more complex, but you can throttle them up and down, steer them, and even restart them in space. For that initial liftoff, though, nothing beats the raw power of solids.
So now that we're moving, we run smack into our second problem. And it's a direct result of that rocket equation we talked about. Carrying dead weight is the absolute enemy of speed.
The logic here is pretty simple, right? Why would you carry an empty fuel tank all the way to orbit? The answer is, you don't. And this is the genius of staging. It's a solution where a rocket literally sheds pieces of itself as it climbs, getting lighter and more efficient with every piece it drops.
Let's see how this works. At liftoff, the whole vehicle is at its absolute heaviest. The boosters and the first stage core are firing with everything they have, fighting against this incredible inertia and gravity's constant pull, but they're not going to be needed for the whole trip.
After just a couple of minutes, those boosters and the first stage have burned through all their fuel. They've done their job. But now, their huge, empty structures are nothing but dead weight. They're an anchor, holding the rest of the rocket back. They have got to go.
And just like that, they're dropped. With all that mass gone, the rocket is suddenly so much lighter. A special adapter gives a clean separation, and the upper stage engine kicks on. Now you've got the same amount of thrust, pushing a much smaller vehicle. The result? A massive jump in acceleration, making it way easier to hit that final orbital speed.
As we accelerate, we face our next challenge. We're not in space yet. We still have to punch through the thickest part of the atmosphere at hypersonic speeds, and that creates this fiery, high-pressure gauntlet for our satellite.
The hero here is the payload fairing. It's way more than just a nose cone. It's a high-tech shield. It's shaped to slice through the air, and it's built to handle incredible heat and pressure. It also acts like a little mobile clean room, protecting the satellite's sensitive gear from any contamination.
But hey, remember our rule about dead weight? Once the rocket gets high enough that the atmosphere is basically gone, the fairing has done its job. It's now just extra mass. So it gets jettisoned too, usually splitting into two halves like a clamshell and just falling away.
So now we're in the near vacuum of space. The challenges of brute force and fighting the atmosphere are over. The game has totally changed. Now it's all about structural efficiency and absolute pinpoint precision.
This is where the upper stage shines. Its engines are different. You'll notice that huge bell-shaped nozzle. That's designed specifically to be super efficient in a vacuum where there's no air pressure. Its job isn't raw power, it's surgical precision.
It performs the final burns that put the payload into the perfect orbit.
But to be efficient, these upper stages have to be unbelievably light. The tanks on the Centaur upper stage, for instance, were so thin they were literally described as paper thin. Without any fuel inside, they were so flimsy they could actually collapse under their own weight. So how could something so fragile possibly survive the forces of launch?
Well, the answer is just an incredibly clever idea: pressure stabilization. It works just like a party balloon. When it's deflated, it's just this flimsy piece of rubber, right? But as soon as you inflate it, that internal air pressure makes it rigid and strong. Rocket engineers did the exact same thing, using the pressure of the fuel itself to give those ultra-thin tanks all the structural strength they needed.
And finally, we get to the climax of the whole mission. After all that fire and fury, the very last step is all about quiet precision. Once the upper stage is in the perfect spot, a high-tech belt holding the satellite in place, called a clamp band, is released. There are no more explosions, just a set of springs that give the satellite a very gentle, precise push, sending it on its way to start its own journey.
So, as you can see, getting to orbit is really a series of what seem like impossible problems, and each one has its own incredible solution, all happening in a perfect sequence.
What this all really shows is that a rocket isn't just one single machine. It's an entire orchestra of systems. You've got the boosters providing that deafening opening blast. The stages perform their powerful solos and then just gracefully exit. The fairing shields the main star, and the upper stage provides that delicate finale. Every single part has to perform its job flawlessly, at the exact right second, for the mission to succeed.
Every single piece of a launch vehicle, from those massive boosters down to the tiniest spring in the deployment mechanism, represents a clever, hard-won solution to a problem. It's really a testament to what we can engineer, which, makes you wonder, what's the next impossible problem we're going to solve?